So this is Iteration Revisited, and this is really, it's a talk in two parts. So the first part is about the iteration scheme that we have in C++ these days, and about a few problems that might occur with that, and some ideas for how we can do things better. And then the second half is about a library that I've written that sort of explores these ideas. You might have heard a couple of other people mention it this week, or you might have seen my lightning talk last night. So the second half of the talk is kind of about the library itself. Okay, so that's what's on the menu. Is that okay with everyone? Yeah, some thumbs up. Excellent. Because it's kind of too late to change it now. Okay, Iteration Revisited. So let's start by revisiting probably the first loop, the first bit of iteration that many of us wrote in C++. Or in C, or probably pretty much whatever language you started with. You might have written a loop that looks something like this. Okay, this is kind of the interesting bit. So what we're doing is we're initializing some index I to 0. We're continuing while I is less than the size of the array. We're accessing the ith element of the array and calling, doing something with it. And then we're incrementing the index at each step. Okay, so again, this is kind of the first loop that many of us wrote. You could write this in a different way as well. And perhaps if you came from a C background, you might have decided to write it like this. Okay, so we can iterate an alternative way over our array. We can initialize a pointer p to the address of the start of the array. We can continue while p is not equal to the address of the array offset by size elements. We can access the elements by dereferencing the pointer, and we can bump the pointer at each step. So you could iterate over an array like this. Actually, these days, you'd probably write it something like this instead. So now we've got standard begin and standard end. Standard end's really handy because for an array of known bound, we don't need to keep that size parameter ourselves. It will work it out. But actually, you probably wouldn't even write this today. You'd probably write something more like this. And perhaps you'd probably go even one step further and write a range for loop, right? But a range for loop is kind of syntactic sugar for something like that, not precisely this, but something very close to this. Okay, so if I can go back, I kind of like this little progression, this little animation here, because it really emphasizes something to us about iterators. And that is that STL iterators are a generalization of pointers to arrays, array pointers. Okay? STL iterators are based on pointers into arrays, and in fact, array pointers are the most powerful kind of iterators. They're contiguous iterators. And this is what we've had in the STL for, well, I mean, since the first C++ standard, and it was a standalone library before that, for a very, very long time now. And there are certain advantages to this scheme. First and foremost, this is a very, very powerful scheme. We can go all the way up to random access, contiguous ranges even. We can write, pretty much all the algorithms that we can think of that sort of need to linearly iterate over a sequence. We can write them using iterators. They're very, very powerful. They're also low overhead. So this was particularly important back in the days when compiler optimizers weren't anywhere near as sophisticated as they are today. But even today, if you go and you write some code using iterators and you plug it into Compiler Explorer, you'll see that all the iterator gunk kind of goes away. Iterators are really low overhead. Another advantage, this one's maybe a bit more arguable, but iterators kind of have a natural syntax. Iterators use the same syntax as built-in pointers do. So if we want to be C++ experts, we have to understand how built-in pointers work. And if we know how built-in pointers work, we know what iterators, we know how iterators work. We know what iterators do. So there are a lot of advantages to iterators, but there's a pretty big disadvantage as well. And that is that iterators are just as dangerous as raw pointers. Because they're based on raw pointers, iterators are just as unsafe as raw pointers. Okay, so at this point, I've started using words like safe, unsafe, dangerous. And so there's an important question we need to ask, which is, what do I mean by safety? Because if you went to Timur's talk yesterday, safety means different things to different people. So what do I mean by safety? So the definition I really like comes from a talk by Dave Abrahams, gave at CppCon last year. So Dave Abrahams, very well-known name in the C++ world, went to work at Apple on Swift for many years. Now he's back, he's working on a language called Val, aims to be a memory-safe language based on mutable value semantics. And Dave gave this talk at CppCon last year, and he used this definition of safety that I really like. He says, a safe operation cannot cause undefined behavior. So that might be a little bit small on the screen, so let me blow that up a tiny bit. A safe operation cannot cause undefined behavior. Right? Because as soon as we have undefined behavior occurring in our program, all bets are off. We can no longer reason about the state of our program. I'm sure you've all seen these kind of crazy examples. People like to give them at lightning talks or put them in on Twitter about how, you end up calling, say, some completely different function that you never wrote, or you get some completely unexpected behavior as a result of undefined behavior. If we want to reason about our programs and how they work and what they're doing, we need to avoid undefined behavior at all costs. Really, we can't start to reason about any other kind of safety until we have eliminated undefined behavior. Okay, so this is the definition of safety that I really like, of definition of a safe operation. So let's look at some code using iterators and decide whether those operations are safe operations according to this definition. I think maybe you can sort of guess where this is going to go, but let's have a look. Okay, so first of all, I'm initializing an iterator to point to the past the end position of some range. Okay, this is perfectly fine. What's not perfectly fine is the next line. On the second line, I'm performing the dereference operation on a past the end iterator, and dereferencing a past the end iterator is undefined behavior. Okay? So, what if instead of dereferencing the iterator, what if I increment the iterator? So I have my past the end iterator, it's in the terminal position, and then I decide to call operator plus plus on that. A whisper from the front, undefined behavior, incrementing a past the end iterator is UB. And if you think about these in terms of array pointers, the language says we can form a pointer to the address that's one past the end of an array, but we can't form a pointer any further. It's just banned by the language. We can't form arbitrary pointers. So we can't increment past the end of a sequence of a range. If we have a begin pointer and a bidirectional range, we can't decrement the begin pointer. Again, that's undefined behavior. If we've got a random access range, we can't do random access jumps outside of the range. That's undefined behavior. Okay. All right, next example. So here we've got a function called min_iter. It takes reference to a vector, and then it just calls min_element to return an iterator that points to the minimum element in this vector. Okay, so I guess somebody didn't like all that vec.begin, vec.end stuff, so they wrote a wrapper function that just takes a vector and calls min_element. So unfortunately, the way that this is written, if we have a function called getVector and it returns by value, that temporary vector is going to bind to the const reference. We're going to call min_elements. That's fine. Min_element is going to return an iterator into the vector. That is fine. We're going to save the returned iterator in this iter variable. But then the bad thing happens, because then we hit the closing semicolon, the end of the statement, the end of the full expression is the technical term, and at that point, the temporary gets destroyed, and now our iterator is a dangling iterator. And if we try and dereference that dangling iterator as we do on the last line, you guessed it, undefined behavior. So dangling iterators can occur easily, and pretty much any operation we try to do on a dangling iterator is UB. We're allowed to destroy it, we're allowed to reinitialize it with assignment, but any other operation, anything useful with it, is going to be undefined behavior. All right, one last example. This one really, I hate this one. Okay, can anybody tell me what's wrong with this code? Reallocation, yeah. Iter is not valid as soon as you call pushback. Absolutely, yeah, we get iterator invalidation. But you know, that's okay, because we're gonna write this code and the first time we test it, it's immediately gonna crash and we'll know we've done something wrong, right? Right. This code might work perfectly well. All right, so let's actually look at what's going on here, right? So we're initializing an iterator with vec.begin. This is effectively going to give us a pointer to the start of the vector's internal storage. Okay, then we call pushback on the vector, and if the vector happens to be full at that point, this is going to cause the vector to do a reallocation internally. So it's going to allocate a new array, it's going to move everything from the old array into the new one, and it's going to delete the old array. And suddenly our pointer that was holding the address of the start of the old array is now a dangling pointer, a dangling iterator. It's been invalidated. And so when we try to compare our saved pointer to the end of the new array, that's undefined behavior, right? The language says we can't compare pointers from different arrays. It's not allowed. And what makes this particularly insidious and what makes me hate this example so much is that there's nothing obviously wrong with this code, right? I'm sitting here at a C++ conference, or standing here with a room full of C++ experts who I'm sure recognize this and know that this is wrong. But not everybody who uses C++ is at that expert level, or has to be, should be at that expert level, right? Code like this, I think, should work. And what makes it even worse is that this code will work most of the time, right? You can have this sitting in your code base for 20 years and it works perfectly well because it just so happens that whenever you call it, the vector doesn't need to reallocate. But then all of a sudden, one day, you recompile, your standard library has decided to change its vector implementation, so now vec happens to be full at this point, and now you're getting undefined behavior when you never did before. Or maybe somebody changes something like 1,000 lines away, and the vector's a slightly different size coming into this code, and suddenly its pushback is reallocating when it didn't before, and you're in UB land when it's worked perfectly well for 20 years. You can tell, this one, I don't like this. So iterators can become dangling in non-obvious ways, right? As I say, just by inspection, if you don't kind of know how iterators and vector work behind the scenes, there's nothing that jumps out at you as bad about this. It's all part of the C++ experience, right? This is how you become a senior developer. This is how you get to go to conferences because you know about things like this. So, okay, our statement was a safe operation cannot cause undefined behavior. But as we've seen, most iterator operations can cause UB. And so if you put these two statements together, really there's only one conclusion we can draw, which is that STL iterators are a fundamentally unsafe abstraction. And this is kind of becoming a big deal. If you've seen Timur's talk yesterday, if you've seen a lot of talks at other conferences recently, people are really starting to care about safety in C++. We've had the NSA coming out and saying, don't use memory unsafe languages, which I find strange because I thought they would like it if we could get hacked. But anyway, we've had senior people at companies like Microsoft coming out and saying, don't use memory unsafe languages, avoid C and C++. And it's because of things like this. So, can we design an iteration scheme that avoids these problems, that avoids this unsafety, avoids this undefined behavior? Well, in order to think about how we might do that, let's look at what we would need such an iteration scheme to be able to do. Okay? So we're going to go back to this code, and let's look at the fundamental operations that any external iteration scheme needs to be able to do. So there are 4 operations. We can see them all on this example. So first of all, we need to initialize some iteration state. We need to be able to hold onto some state that tells us where we are in our sequence. So for iterators, this is stored in the iterator object, but in general, we need some iteration state. We need to be able to check whether iteration is complete. And again, for iterators, as we know, we compare it against the pass end iterator or a Sentinel in C++20. We need to be able to read the element corresponding to the state. Okay, if we can't do that, well, we can't do anything very useful. And finally, we need to be able to advance our iteration state so that we are now looking at the next element in the sequence. Okay? So these are the fundamental operations, the basis operations that we need for any iteration scheme. You know, we initialize some state, and then we do check, read, advance, check, read, advance in a loop until such time as the check tells us we're done. Okay? Initialize, check, read, advance. Now, what's quite interesting is that although these operations are essential and fundamental, they don't actually have to be implemented as 4 separate functions. Right? We can fuse these operations together in certain ways. And some of you might be familiar with the Rust iteration scheme. So the way it's done in Rust is that they fuse together the check, read, and advance operations into a single function called next, and next returns, in C++ terms, an optional t. So the first time you call next, it returns you an optional containing the first element, second time, an optional containing the second element, and so on until eventually iteration is complete and it returns you an empty optional. Okay, so that's the Rust scheme, and this has some advantages, chiefly that it's much simpler than the C++ scheme, right? There's only one function we really need to worry about. But there are some downsides to this as well, namely that we lose some expressive power that we have with the C++ scheme. There are algorithms that you can't write with the Rust scheme, and there are algorithms that you can't write as efficiently as you can with C++ iterators. So if we want full generality, if we want to be able to do all of the things that C++ iterators can do, we do indeed need to implement these 4 operations as separate functions that can be called individually. So if you're interested in this stuff, I really, really, really highly recommend this talk from Barry Revsin. He gave it as a keynote at CPP Paris a couple of years ago. This is an absolutely fantastic talk. He compares the C++ iteration scheme to D ranges, to Rust iterators. He talks about Python, C#, Java. It's a really, really, really amazing talk. So highly recommend that one. But okay, we know what we want our iteration scheme, what we need it to be able to do. We need to be able to provide these 4 operations: initialize, read, check, advance. Can we think of some sort of iteration scheme that maybe we're already familiar with, that has all these properties, but that is safer than iterators? Well, yes, we can. And actually, every single person in this room and every single person watching online is already familiar with this. And I 100% guarantee that you're already familiar with it because it was the very first slide of this talk. That is iteration with indices, indexes if you prefer. Okay, so let's have a look at this for loop. Very similar one to what we saw on the very first slide. Let's have a look at what we're doing here. Well, first of all, we're initializing some iteration state. Okay, our iteration state this time is our index I, size t index. Checking whether iteration is complete, we're checking whether I is less than the size of the vector. And now we're defining our read operation to be bounds checked access to the vector, okay? This is how we're defining our read operation for our new iteration scheme. And then finally, our advance operation, we're just going to increment the size t. Okay, so these are the definitions of the operations that we're going to work with. So now what we're going to do is we're going to take those iterator UB examples we saw earlier, and we're going to substitute in our new operations and see what happens. Okay, so here was the first example. We were initializing an iterator to the end of the array and then dereferencing that iterator. Well, the equivalent with our new scheme is we initialize an index to the size of the vector, and then we call our read operation vec.at. And what this is going to do is it's going to be bounds checked, it's going to throw an exception. Now, maybe exceptions aren't what you want, but the point is that this is well-defined, right? We're not reading arbitrary memory, right? This is well-defined operation, we're not getting UB. And what if instead of doing our read operation, we call our advance operation? Well, index is just a size t. So we're just calling operator plus plus on a size t, which is well-defined for, size t is unsigned. It's well-defined, If somehow you have a vector that is size t in size, I'm not quite sure how you managed it, but even if you do, this is not undefined behavior. Incrementing a past the end index is fine. Assuming we have unsigned indices, or if we use signed indices, we have some sort of checked operation, but we can do that. What about our third example? So this is where we had that min-iter function. Well, we can replace that with a min-index function. It's only a couple of lines, the implementation, but it's not really relevant, so I just skipped it. But what min-index does is it iterates over the vector, and it returns us the index, that is the state corresponding to the minimum element in that vector. Okay, so now we do what we did before, and we call it with a function that returns by value, and it returns us the index of that vector, of the minimum element of that vector, and then at the closing semicolon, the temporary gets destroyed, and then it's fine. Okay, we're holding on, we've got a size t, index, sure, but that's it, right? We can't even perform our read operation because we no longer have the vector around to call the read operation on it, right? It's gone. So dangling indices, that is the equivalent of dangling iterators, are not possible sort of by design. Well, they can dangle, but we can't do anything with them, right? So a whole class of bugs just kind of goes away. So what about the last example, the one I really hated? So here's the equivalent substituting on our new operations. So now we're initializing an index to the 0 position. Now we're doing a pushback operation, and even if pushback reallocates, we're fine, because we can still compare our index with the size of the array. That's perfectly well defined. This is going to work, and we're not going to have undefined behavior. Index invalidation problems are no longer UB. Now, okay, in this particular example, we're not going to invalidate the index. You can still invalidate indices in sometimes. You could be holding on to index number 100, and then you resize the vector so it's only got 50 elements, and your index is invalid. But in that case, you're going to catch it at the next read operation because the read operation is bounds checked. So index-based iteration dramatically reduces the potential for undefined behavior compared with using pointer-based iterators. But it's still just as powerful, right? We can still do random access with indices. All the algorithms we could write with C++ iterators, we can still write using index-based iteration. So here's the big idea. What if somebody wrote a library that generalizes the idea of iteration by index rather than iteration by pointer? So the STL generalizes the notion, starts with pointers and generalizes that. What if we started with indices and generalized from there instead? What if somebody did that? Wouldn't that be lovely? Did I do that? Yeah, funnily enough, I did do that. So, getting some echo. So Flux is a library that I've been working on for, on and off for about the last year or so, that's kind of exploring these ideas. It started off as just kind of a proof of concept. Like I had this idea of like, what if we used indices, literally in the shower one day. And I kind of sat down and started writing some code kind of as a proof of concept. And it just kind of grew and grew until it turned into something that I think is pretty good. So I thought I'd come and give some talks about it. So Flux is the name of the library. It's a C++20 library. The URL is there. The name is not particularly relevant. The important thing about the name is that it's got an X in it, which makes it sound all cool and mysterious. So what are the aims of Flux? Well, first and foremost, we want much improved safety by default compared with using STL iterators, for all the reasons we've just been looking at. While we're there, I've been using iterators for a long time. I've been using C++20 ranges since it was the ranges TS. I kind of know about the rough edges and the things that aren't quite so great. So maybe while we're working on this, we can smooth out a few of those rough edges as we go. One of the other aims of Flux is that we'd like to provide runtime performance that is at least as good as C++20 ranges, so that if you can afford to use ranges, you can afford to use Flux. And finally, Flux aims to offer compatibility with existing STL code, right? So STL's been with us for 25 plus years. There's countless millions, possibly billions of lines of code out there using this, so I can't just tell everyone to throw all that away and start using the new stuff. We have to offer some sort of compatibility story. So we're going to look at that as well. Okay, so we know what our iteration basis operations are, right? Initialize, read, check, advance. So how do we write these things in Flux? How do we spell them? Well, our initialization operation, we call it Flux first. Okay, so I couldn't call it begin for obvious reasons. So what's a synonym for begin? First. So first returns you an object called a cursor. So a cursor is a generalization of an index. So just as an iterator is a generalization of an array pointer. So I didn't want to, the term index has really strong associations with like an integer value. So I didn't want to reuse the term index, so I used the term cursor. But it just so happens for contiguous sequences, it is literally just an integer. And if in the following code, if you just want to sort of mentally substitute the term index for cursor, then you'll have absolutely the right idea. So this is our initialize operation. Our check operation is spelled isLast. So we ask the sequence, is this cursor a past the end cursor? Should I stop iterating now? Okay. Our read operation, very simple, it's called read at. And this says to the sequence, please will you give me the element at this cursor position? And importantly in Flux, our read at operation is bounds checked. Okay? Actually, by default, if the bounds check fails, it's going to terminate your program. You can configure the library so it can throw an exception instead. One of the two things will happen. Finally, our advance operation, we spell that just inc. So this takes the cursor by reference. It says to the sequence, please will you update this cursor so it points to the next element. And you'll notice actually all these operations, particularly the last three, they take the sequence we're operating on as their first element. As their first argument. Meaning that if we're in the case where we had some temporary that has now been destroyed, as we saw in an earlier example, it means we can't actually call any of these operations at all. All we're left with is a cursor object that we can't use, and we just have to wait for it to be destroyed. So as I was saying, the dangling iterator problem just kind of goes away just as by virtue of the design of these operations. So, as I mentioned, Flux is a C++20 library, makes pretty heavy use of concepts. So, a type that provides implementations of these 4 operations, we say that it models the sequence concept. Okay, so again, I didn't want to reuse the term range, that would be confusing. So in Flux, we call it a sequence. So again, if you want to do a mental substitution, then just a sequence equals range, if you like. Like the STL, sequences are assumed to be single pass by default. That means that once we've read an element, and once we've incremented the cursor, that element has gone, never to return, right? So things like input streams are like this, input ranges in general. But like the STL, we also have multi-pass sequences. So STL calls these forward ranges. In Flux, they're multi-pass sequences. And what multi-pass sequences mean that once we've iterated over our sequence, we can, start again from the beginning and read the elements again, or maybe we can have multiple cursors going at once, reading the elements, and that's perfectly fine. So most sequences actually are multi-pass, including, all the containers that you can think of. So multi-pass sequences have some additional requirements on their cursor. Single-pass sequences, we have very minimal requirements on the cursor. It needs to be movable, and we kind of assume that the move operation is cheap. But beyond that, a single-pass sequence can use any cursor representation, internal representation that makes sense to that sequence, right? For multi-pass sequences, we have some additional requirements. Namely that the cursor type needs to be a regular type. So a regular type is one that's default constructible, copyable, and equality comparable. So if your cursor has these properties, so a multi-pass sequence requires these properties of the cursor, and conversely, if your cursor has these properties, we assume the sequence is multi-pass, because it turns out that kind of semantically, single-pass sequences, the cursors should be move-only, right? But I didn't want to require move-only because, requiring something not to be copyable is weird, so I didn't do that. So if you happen to have a copyable cursor, but your sequence is only single pass, then you can opt out. This is kind of the opposite default to ranges. Yes?
What is the idea? How does this approach of indices works with, for example, container-like unordered map?
How does it work with a container like unordered map? How can you do these things with, so node-based containers in general, something like a linked list? It's difficult to do in a safe way, right? So it's tricky to do it to provide guarantees against undefined behavior, because pretty much you want to you need to kind of, how do you ensure that your next pointer is still valid? How do you ensure that there is still an object at this particular address? That's, in general, something that's very difficult to do. There are a few different techniques. If we've got time at the end, remind me, I'll go into it in a bit more detail. It is possible. There are a few different techniques that you can do it. But yeah, remind me at the end if we have a couple of minutes. Okay, so we have single-pass sequences, we have multi-pass sequences. We can go further. We can have bidirectional sequences. So like bidirectional ranges, we can have bidirectional sequences. And these are sequences which additionally allow their cursors to be decremented. So we have a function flux dec counterpart to inc that moves the cursor back one place. Going even further, we have random access sequences. So these are sequences, they provide 3 additional operations. So first of all, we've got an overload of inc that can apply an arbitrary signed offset, so you can jump around within the sequence in constant time. Provides a distance operation, so if you've got 2 cursors into your random access sequence, you can ask how many elements are there between these 2 positions. And finally, cursors for random access sequences must be totally ordered. That is, they must provide all of the less than, greater than, etc. operations so that we can ask, like, is this cursor position earlier or later in a sequence than this cursor position? So bidirectional sequences like bidirectional ranges, random access sequences like we have random access ranges, and we also have contiguous sequences. These are the random access are backed by some contiguous in-memory array. It means we can do low-level things like memcopy and things like that. So armed with these concepts that are, as you can tell, sort of direct analogs of the equivalent concepts in the existing ranges library, we can go and we can implement all of the same algorithms that you could write with iterators. Okay? Because, you know, it's almost a mechanical translation from one to the other. So the Flux algorithm, how many algorithms is it in the STL now? It's over 100, right? I think 105, something like that. It's quite a few. It's a lot. We don't have all of them in Flux yet. One day I would like to. We do still have quite a few. So as of right now, these are the algorithms that we have in Flux. A few of them are the same ones as the standard library with slightly different names. So we don't quite have parity in terms of algorithms, but you know, we're still got quite a few. And if you're watching this on YouTube at some later date, hopefully we'll have a few more as well. So okay, with these concepts, with these operations, we can write all of these algorithms, and that's really nice, right? But that kind of puts us in the same position, the same place that the STL was in 1998. C++20 came along and it expanded what the STL could do. It offered pipelines. It offered these range adapters, things, people call them views, things like filter and transform and so forth. So we could build up these C++20 ranges pipelines. And if you've seen any of my talks before, you'll know that I'm a huge fan of C++20 ranges. And I'm a huge fan of this style of programming, of people call it sequence-orientated programming or collection-orientated programming, building up these pipelines of operations. So C++20 ranges allows that, and of course, I wanted to provide that functionality in Flux as well. So like C++20 ranges, Flux provides a variety of sequence adapters that perform lazy evaluation in exactly the same way as things like views filter, views transform, views chunk by, views, you know, all of those. And as with ranges, we typically compose these into pipelines. So a pipeline begins with some data source, some sequence. We pass it through 0 or more adapters that set up how our data is going to be read, right? So the adapters in the setup process, they don't do any actual work. They just set up how the iteration will occur. And then finally, we call some algorithm that actually does the iteration, and at this point, the adapters, you know, do their thing. So this algorithm might be one of the named algorithms in Flux that you've just seen. It might be an algorithm that you yourself as a user have written. It might be a standard library algorithm, as we'll see shortly. It might just be a for loop, right? Because, and I got in trouble last time I said this, but I'm going to say it again, right? So Tristan's law, every for loop in your program is an ad hoc, unnamed, unspecified algorithm on some sequence, right? So every for loop is an algorithm, you just haven't given it a name. Which doesn't necessarily mean it's bad, maybe it is genuinely just one-shot code you're never going to need again, and that's absolutely fine, but you know, maybe if you're writing very large for loops, maybe start to think about that. No raw loops, as a wise man once said. So okay, let's have a little look at the syntax of Flux. Let's have a look, finally have a look at an actual example of some Flux code. Okay, so we're going to start off with a vector of integers, and then what we want to do is to find the maximum of the squares of the even numbers in this vector. This is a function that has absolutely no practical use, but is very useful in slide code, and just because it gives you a flavor of the different operations in Flux and how they're written. Okay, so the first thing that we need to do in Flux is we need to decide how we're going to iterate over our source sequence. So do we want to take a copy of the vector? Do we want to move the vector? Or do we want to iterate over a reference to the vector? Okay, so in this particular case, I've decided I don't want to copy the vector, I don't want to move it, I'm just going to iterate over a reference to the vector. And then I'm going to apply a filter adapter. So this is a filter adapter that we're passing it one of the built-in predicates that says I want to retain the even numbers. And right away you notice there's quite a difference from C++20 ranges because the way we compose operations in Flux is using the dot syntax, the member function syntax, right? As opposed to C++20 where you'd use like pipe, standard views, filter, blah, blah, blah. Okay, so I've got to be honest, there's no technical a reason for using member functions as opposed to pipes. I could have used pipes in Flux. It would have been, it wouldn't have been easy, but it wouldn't have been all that difficult to use the pipe operator in Flux. The thing is, I just find that the dot syntax just makes your source code just so much more readable than having like pipe standard views transform, pipe standard views, blah, blah, blah. Right? It just reads so much nicer, so much more nicely. And, readability in source code it's not zero value, right? It is important. And there's another advantage actually, that when you're coding this in your IDE, when you write flux refvec and you hit the dot key, hit the full stop key, and your IDE gives you a nice long list of all the operations that you can apply. And it even gives you like a little bit of help text as well. So this is not something that your IDE can do, maybe they'll get smart enough, but it's not something in general your IDE can do if you just type the pipe, the bar character. So it's another advantage as well. So all right, we're applying a filter to take the even numbers. The next thing we want to do is apply a transformation to square each integer. So in the standard library, this operation is called views transform, but literally every other library of this kind in the entire world calls this operation map. So Flux takes the majority view and calls this operation map as well. So we've got our source, we've got a couple of adapters, we want to call an algorithm. In this case, the algorithm we want to call is max. So we're going to find the maximum value in our adapted sequence. Okay, but there's actually a bug in this code, right? Well, apart from the missing semicolon. There's actually a problem with this code as it is on the screen. If you imagine the semicolon was at the end. Anybody? Overflow? No overflow? Oh, well, I guess, yeah, okay, the integer multiplication might overflow, but let's assume it doesn't. So let me ask, what if the vector only contained odd numbers? What result am I going to get? Nothing, right? Because how do we, if we've got an empty sequence, or even if the vector was empty, right? What's the maximum of an empty sequence? Well, that's kind of a difficult question to answer. So the standard library actually, C++20, there is an overload standard ranges max that takes a range. Can anybody guess what happens if you pass standard ranges max an empty range? Magic words, yeah, you get undefined behavior, right? Undefined behavior for standard ranges max. Flux, we want to avoid undefined behavior as much as possible. So in Flux, actually, max returns you an optional. So if the source is non-empty, then it gives you an optional with the maximum value. Otherwise, if the source was empty, it gives you an empty optional. So we avoid undefined behavior, and you as the user get to choose what happens if the source is empty. We kind of force you to handle it. So in this particular case, I've decided that 0 is a reasonable default. So we write the pipeline like this. Actually, if we wanted to, we could write it in a slightly different way. We could write it like this instead. So Flux has this underscore function, and what this allows you to do is if you have custom Flux sequence adapters or custom Flux algorithms, you can incorporate them into a pipeline like this. So, okay, for the built-in filter, max, etc., we have kind of the shortcut, but this allows you to use your own custom operations in a Flux pipeline as well. Okay, so Flux comes with a whole bunch of, sorry, yes, question. So no, there's no allocation going on here whatsoever. How does it work if, right, so we're not allocating a new vector at any stage. The way this works is that the max algorithm, what it does is it says, okay, I want to initialize my iteration state, and so it calls the initialize operation on the map, which calls the initialize operation on the filter, which calls the initialize operation on the vector, right? And then it says, okay, I want to do my end check, and it calls the end check on those. And then it says, eventually, it says, I want to do my read operation. And the read operation says, okay, I'm going to call read on the map, which is going to call read on the filter, which is going to call read on the vector. So I'm going to get a value out of the vector. If that element is even, then that's going to be passed to the maps read operation. The maps read operation is going to square it, and then that's going to be passed to the max algorithm. So it's the same lazy evaluation procedure, like precisely the same evaluation procedure that C++20 ranges does, except adapted for these safer Flux operations. But it's kind of the same principle going on behind the scenes. So,
what happens if you put the get vector inside the ref thing and then return temporary? Does it detect that? Or, well, it's fine on that line, but...
So if you tried to pass an R value vector into Flux ref, it's not going to work. Right? Compile error.
So you were saying that you do like your sort of check, then you do an increment, then you do a read, and it goes all the way up through the filter. But if filter is going to filter at that value, it's going to return nothing. Does that mean something like filter would another?
Yeah, so actually it's a bit more complicated than I said, right? So when we call so map calls the advanced operation on filter, and what it does at that point is it skips ahead until it finds an even element from the vector. Yeah. So if you saw my lightning talk last night, you would have seen like kind of what filter's doing behind the scenes. Okay, so Flux comes armed with a whole bunch of these lazy sequence adapters. I thought we had parity with C++23 ranges. It turns out there's one I forgot about. So there's one adapter that is in C++23 that is not in Flux yet, but it will be very shortly. But other than that, we've got everything that's in C++23. As far as I know, everything that's been proposed for 26 and a few more besides. We've got loads, and this list is always growing because I love this stuff. So we're going to have lots and lots of these. Okay. Ranges compatibility. So as I mentioned, ranges have been with us, or the STL has been with us since the very start, for as long as C++ has been around. So we need to have some sort of compatibility story. We can't just tell everybody, throw away your code, rewrite it in Flux. It might be slightly more successful than rewrite it in Rust, but maybe not. Right? We need to have some sort of compatibility story. So first of all, if you have a C++20 contiguous range, you can just use it with Flux. You don't have to do anything whatsoever. And we just saw an example of that on the previous slide, right? So every contiguous range is automatically a Flux contiguous sequence. We have a blanket implementation for size contiguous ranges, so you can just use them in Flux without having to do anything whatsoever. The reason we can do this is because if you have a contiguous range, we can just cheaply index it. We can get the data pointer. We can offset from there. We can do bounds checking. So every contiguous range is a contiguous sequence. This covers vector, array, string, string view, span, initializer list, C arrays, what have you. You can just use them right away with Flux. For other kinds of ranges, so apparently people occasionally like to use containers that aren't vector, which seems weird to me, but apparently people do it. So for other kinds of ranges, we have a function called fromRange. And what this does is it takes your range and it wraps up the iterator operations in the equivalent Flux operations so that you can call all the Flux algorithms, use the Flux adapters with your range. Now, because we have to call the iterator operations, these are like unsafe, as we saw. So we get, we kind of, if we're using fromRange, we don't get the same safety guarantees, which is a bit of a shame. It's no worse than using ranges directly, but this is kind of, it's just so that we have compatibility. It's the best we can do, the best we can manage. So contiguous ranges, perfect, use them straight away. Other ranges, we have this fromRange wrapper function. So you can use all of your current range implementations, you can start using them with Flux algorithms, with Flux sequence adapters to build up these pipelines. But what about going in the other direction? What if I have a Flux sequence that I've built up, maybe through some adapter chain? I've got a Flux sequence and I want to use it with some code that's expecting an STL range. Well, here the news is even better, because every Flux sequence is an STL range. It provides STL C++20 compatible begin and end operations. So we can use them with C++20 algorithms, C++20 range adapters if you want to, for some reason. And in particular, we can use Flux sequences with range for loops, right? So you can just do like for int I colon my Flux sequence, and it's just gonna work, right? So how do we achieve this? Well, we have this class called sequence iterator, and what it does is it takes a pointer to a Flux sequence, and it takes the current cursor position we're looking at, and then it goes and implements all those, however many there are, dozens and dozens of operator overloads that are necessary for iterators, and it implements those in terms of the equivalent Flux operation. So this is, like, it's holding a pointer to the sequence, it can dangle, it's not safe, but it's iterators, we're used to that. Okay, so ranges compatibility, pretty good, I think. So one last section, one last thing I have to talk about, one last thing I have to address that you've all been very politely avoiding looking at, and that's this guy. The elephant in the room, I need to talk about performance, because a couple of times when I've talked about Flux before, and I've said, well, our read operation is bounds checked. And I can see people start to tense up, right? Because as C++ programmers, we're, in many cases, really, really, really focused on performance, right? And the idea of bounds checks kind of gets people nervous. But here's the thing. Compilers are incredibly good at eliding bounds checks in many, many, many cases, right? And part of the reason for this, I think, is that almost all languages written in, like the last 30 years, they use bounds checking universally, right? It's kind of hard to think of a language that doesn't have bounds checking in whatever its native array type is, right? And so compiler optimizers are really, really good at recognizing these patterns. And you can even think of it yourself. If we are calling our end check operation at every step of our iteration, and then the next thing we do is read, and the read is doing a bounds check, the compiler is going to go, well, hang on a second, you've literally just checked this, I don't need to check it again, and so I can remove the bounds check in that case. So let's have a look at a little compiler explorer example. So just in case this is hard to see, I've got a function called count evens. It just counts how many even elements there are in a vector. So I've got this sort of imperative version up there. And then I've got some code that's using a macro called Flux4. It's mostly like intended for testing. But what this does is it uses these Flux primitives, read at, is last, etc., to do the iteration. Oh, sorry. There we are. And actually, if we look at the generated code, we can see that the compiler's decided to lay things out in some different registers. It's not 100%, it's not precisely the same, but the inner loop is a very similar shape. And actually, if you go and you benchmark this code, there is, as far as I can tell, there's no difference between these two approaches, right? The bounds check in the read at operation has completely gone. But this implementation was using this flux4 macro. As I say, this is just something I really use for testing. It's not really intended for end users. Because, well, idiomatic use of Flux, if you can have idioms in a new library, I guess I get to define the idioms, right? So idiomatic use of Flux would be to use a named algorithm where one exists. And in this case, there's an algorithm that does precisely what we want, and it's called countif. And so what happens if we use the countif operation, the countif algorithm, instead of that flux4 thing we were doing before? Well, if we do this, now we get 100% precisely the same, byte for byte, identical code as with the original imperative version. Right? So if you came to my lightning talk last night, you probably know what's going on here. What's going on is that Flux has this extra feature called internal iteration. So this is an optional extra customization point that Flux sequences can implement. Currently it's called for each while. That name might be changing, but the way it works is that we have this function for each while. It takes some predicate, and what the for each while function does, it instructs the sequence to iterate over its elements in the best way that it knows how, until such time as the predicate returns false. And it turns out that many sequence implementations and many sequence adapter implementations can perform this for each while, iterate over all your elements more efficiently than by this chain, as we were talking about, this chain of read calls, this chain of check calls, this chain of is-last calls. So many sequence implementations can do this nice and efficiently, and it turns out that many, many algorithms can be written in terms of a call to this for each while function. Fold, find if, min, max, all, any, none, loads and loads of algorithms you can write in terms of this for each while primitive. So if you combine these two things, then in many cases, Flux pipelines can generate more efficient code than the equivalent C++20 ranges pipeline. So yeah, we can have a look at an example. So here I've got C++20 ranges pipeline. We're taking the vector, we're filtering, retaining the even elements, we're squaring each element, kind of similar to what we saw before, and then we're summing up all of the even squares using standard accumulate. Okay, so this is a version using a C++20 ranges pipeline, and here's the equivalent Flux pipeline. So again, we're iterating over the vector by reference, we're filtering, retaining the even elements, we're squaring each element, and then we've just got this nice sum algorithm. And now because sum can be written in terms of for each while, we get really, really nice and efficient code. So here we go, the Flux code is on the left, the ranges code is on the right, and you look at this and you go, well, hang on a second. I'm getting a lot more assembly generated on the left-hand side. I'm getting a lot more assembly in the Flux case. But if you look carefully, and maybe the people near the front will prove this, will back me up. If you look at the Flux code on the left-hand side, you're getting all these lovely AVX instructions, right? All these vectorized instructions, because in the Flux case on the left-hand side, the compiler has been able to see through this and actually vectorize the code to use all these SIMD instructions, where on the right-hand side, it hasn't been able to do that. So the Flux version is quite likely to perform better than the equivalent ranges pipeline. Okay, I'm out of time, but I have 2 more slides, so Let's just very quickly go through those. So if we are in this happy case where we can use the for each while algorithm, typically we don't need to do any internal bounds checking because we don't expose any cursors. We're just going from start to finish. We know where the beginning is. We know where the end is. In many other cases, the compiler can optimize away bounds checks. What about corner cases? What if there are cases where you look at your code, you profile, you can see that, okay, this bounds check is happening, it's slowing me down by a tiny percentage, but in this case, that's important. In that case, if bounds checking does lead to an unacceptable overhead, we've got this alternative version of readat. It's called readat unchecked. It does exactly what you think it does, which is to return you the element at a position, but without doing any additional bounds checking. Okay, so the idea is that this can be used selectively. You can profile first. You can always measure, check if this is a particular problem, in this piece of code, then you can switch to using the unchecked version. You can think of it as the equivalent of an unsafe block in other languages. Okay, so I'm out of time. Quick summary of Flux. So that's it from me. There's a couple of links there. Flux, we've got some documentation's kind of work in progress, but there's some there if you want to look at it. That's my Twitter. I tweet about it from time to time. But that's it from me, and thank you very much for listening. Okay, we are at a time, a couple of minutes over, so I guess we can't have any questions on video, unfortunately, and I know it's the lunch break, but I'm going to be here if anybody's got any questions. I'm quite happy to chat for a while. So thank you very much, everyone.